Okay, think we can start right in. What I'd like to do today is just go through some background on water. Some of the properties that we'll talk about today will hopefully allow you to understand some of the concepts we're going to bring up later on when we start talking about pumping and the water table, saturated zone, unsaturated zone, what sorts of things can dissolve in water and cause pollution. A lot of that is going to be based on the background that we're going to go through in the first couple of classes. If you had me for environmental geology, you've seen some of this, but I don't think it's a bad thing to go over things a second time and refresh your memory. So let's just get started on some background. I'm going to write out everything. I'm not going to do PowerPoint presentations with this stuff. One of the reasons is when we get to some of the mathematics, I want to go the same speed that you guys go. And this helps me slow down a lot. If I just put up PowerPoints, I can just blow through those in 30 seconds, and you guys are like writing madly to keep up. I have to write everything you write, so sort of keeps me on pace with you. It's not as pretty, obviously, but hopefully you'll enjoy it. Who knows? All right. Let's start with the first concept related to water, states of matter. In chemistry, we talk about states of matter a lot. The first state that we'll go through is a solid. What's solid water called? Ice. All right, so think of ice. Now, from an atomic standpoint, what does it mean to be a solid as opposed to a liquid or a gas? What are we talking about? What's going on at the atomic molecular level that differentiates a solid from a liquid from a gas? How are they different? So solids have, you're saying, a uniform pattern. What do you mean by that exactly? I like that answer, but elaborate.
The molecules are in a shape that aren't moving.
Okay, so he said the molecules are in a shape that aren't moving. Close, right? So the thing about a solid is that the atoms are arranged in fixed positions. So they can form these geometries. Sometimes they form cubes. Sometimes they form rhombohedron. Sometimes they form tetrahedron. They form these different geometric shapes. So the first thing about solids is that the atoms are in fixed positions relative to one another. And that's where I think your statement, they don't move, sort of comes from. But actually, atoms always move. As long as there's heat, atoms will vibrate. And the higher the heat, the faster they vibrate. And even in a solid, where all these atoms are locked in fixed positions, they'll vibrate in fixed positions. I always use like my class as an analogy. Right now, you guys are solid. If each of you is an atom, my classroom is a solid, because you're all in fixed positions relative to one another. In 10 minutes, you're going to look to your right. He's going to be over there. You look to your left, look behind. Same arrangement of students in here, right? You guys are probably not going to change. But are you moving right now? Yeah, you're wiggling, you're writing. That's analogous to the atoms vibrating because of heat. So they're in fixed positions, but they still vibrate. In response to heat. The second state of matter is a liquid. We tend to call liquid water water. how does a liquid differ from a solid at that atomic molecular level?
The shape that it takes is dependent on what's containing it.
Yeah, so the atoms will move to fill whatever container it can be found in. So in this case, the atoms are not in fixed positions. They can move relative to one another. But they are closely packed. And tend to take the shape of their container. Put water in a milk jug, takes shape of the milk jug. Pour that water then into a bowl, it takes shape of the bowl. Pour it on the floor, it spreads out on the floor. So they're still closely packed together, sort of physically touching one another. They can feel little attractions between the molecules. Water has surface tension and some other properties we're going to talk about. But those atoms can move relative to one another. And finally, we get vapor. What's another name for water vapor? Steam. That's another way we can say it. In this case, the atoms are not in fixed positions. They move rapidly. And they are very loosely packed. So I used that analogy earlier that right now you guys are solid, right? And on break, 20 minutes or so, I'll say, okay, we're going to take a break. You guys are going to get up and mill around, right? You're going to change your positions well enough relative to one another. You might go talk to one of your classmates about another class. You're going to move around the room, but you're still in this rather confined space. At that point, you're sort of behaving like the liquid, right? And then at the end of the class, when I tell you to go home, you guys are going all different directions, right? You're going to your car, you're walking home, you're going to Greeley, I'm going to Fort Collins. We're heading towards the hills, right? In this case, we're moving in much more rapid motion. We're not closely packed at all. And we end up sort of taking the properties of a vapor or steam. All right, any questions on this so far? Okay, so that's just kind of a basic conceptual view of the various states of water related to how they behave at an atomic level. There's a second way that we can sort of look at this, and it's through something we call a phase diagram. You guys have probably seen these if you took mineralogy or petrology. If you had me for environmental, we actually went through phase diagram for water, but we're going to do it again. Now this is going to help illustrate how water responds to the environment, and in particular, how it responds to two aspects of the environment, pressure and temperature. So what a phase diagram does is it shows which state of matter is stable at various combinations of pressure and temperature. Okay, so let's start by creating the basic parts of our phase diagram. So it's basically an XY plot where we have pressure on the y-axis, temperature on the left axis. In this diagram, temperature is going to increase as we move from left to right. So if you're on the left side of this diagram, it's cold. If you're on the right side of this diagram, it's hot. And then on the y-axis, as we said again a minute ago, this is pressure. Low pressure along the bottom of the diagram, high pressure along the top of the diagram. Okay, so think about this for a minute. We have to go back, think about our states of matter and how the atoms are arranged, okay? Where on this diagram would be the most likely place to find vapor, steam, gas? What of these two variables, what's the best combination to create a gas?
High temperature and low pressure.
High temperature, so what does high temperature do?
Relative to the molecule? Or
Yeah, how does it affect the water molecule if it's experiencing high temperature? What's it going to do in response?
It's going to get more excited.
It's going to vibrate a lot, right? And that's going to make it more likely to move around, okay? And then you said low pressure. Why would low pressure be more likely to create a gas?
Well,
There's nothing confining it, right? Nothing's squishing it. It's being allowed to run and move freely, right? So it wants to wiggle around a lot, move around a lot, and nothing's preventing it from doing that. The pressure is not forcing it into a small space. So if you want to create a gas or a vapor, you want high temperature, right side of the diagram, low pressure, bottom of the diagram. So you want to be in this range here. Okay? What about a solid? If you want to create a solid, what's your combination of pressure and temperature that would most likely lead you to a solid state? Solids want to be in fixed positions, right? High or low temperature? Low temperature. So we're going to be on the left side of their diagram. What about pressure? High pressure, right? You want to squish it so it can't move. So the best place to find a solid might be up here. And then sort of in that intermediate area, you might have a liquid. Okay, so our phase diagram for water actually is going to look something like this. Where on the left is the solid field. Anywhere in that field, you're going to have ice. Okay? The vapor field. Anywhere in there, it's going to be steam. That L field. Anywhere in there, you are going to have liquid water. Okay? So let's look at some combinations to try to make this work a little, try to be a little more familiar with what's going on here. So let's say we start right there. Okay? Let's just call this point A. What do I have? Solid, liquid, or gas? I have a chunk of ice, right? Okay. What we're going to do is we are going to increase the heat on this chunk of ice, and we're going to keep the pressure equal throughout this little experiment, okay? So we are going to leave the pressure right here. It's going to stay constant at that level. It's not going to move up, not going to move down. It's just going to stay at that level, and we're going to heat it up, okay? So how are we going to move on this diagram if we add heat? we're going to move to our right, okay? So let's say I add a little heat and I go from A to right here. That's a bad drawing, but you get the point. What do I have there? I still have ice. How is it different from the ice I had at A? It's just warmer. It's warmer ice. You know, when you wake up tomorrow morning, it's supposed to be like 9 degrees or something. And then by 11, it's supposed to be 26 degrees. So if you go out and put your hand on the ice in the morning, it's going to be 9 degrees. In the afternoon, late morning, it's going to warm up a little. It's just warming up, right? But it's still ice. You haven't added enough heat to start breaking the bonds that are holding all of those atoms in fixed positions. Okay? They're just wiggling a little more, right? Let's add a little more heat. We're going to go from A to this point right here. Right on that line. What happens on that line? It's the boundary between solid and liquid, right? So at that boundary, this line right here, we can think of this as the melting line. It starts to melt. At Earth's surface pressure, what temperature is that at in centigrade? 0, 32 Fahrenheit. Yeah, so if we were at Earth's surface pressure, when we add enough heat to bring the temperature up to 0 degrees C, we're going to start having enough atomic movement that all of those atoms that were in fixed positions in the ice, they're going to start breaking their bonds. They're going to be able to move relative to one another. If we add enough heat, we actually move it into this liquid zone, right? Add some more heat. What do I have there? Hotter water, right? And actually you see it's approaching that boundary between the liquid and the gas. So this water's starting to get pretty hot, right? What happens when I hit this line right here? It changes from a liquid to a vapor. That process is called boiling. So this is the boiling curve. What if I keep adding heat? It's going to be vapor, and it's just going to get hotter and hotter vapor, right? Okay, so we end up at B, vapor. This one should be easy to you guys because you've seen it in your lives, right? If you can go home tonight, take an ice cube, put it on a pan, put the pan on the stove, and turn on the heat. Ice is going to warm up, right? Then it's going to melt. Then that water's going to get hot. And then that water's going to boil. And eventually it'll all boil away. And you'll have nothing left in your pan. And all of that water that was once contained in your ice cube is going to be zooming all over in the room. You guys have seen this before. So that's not too hard. All right, let me get rid of this. All right, let's go the other way. Let's start with A. And now we're going to take away some heat. We're going to cool it off. Okay, how am I going to move on my diagram? I'm going to go the opposite direction, right? So start with some hot steam. Take the heat away, it starts cooling off, right? Cool, 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 cool. What happens when it hits that line? It turns into a liquid through a process called condensation, right? So not only is this the boiling line, it's also the condensation line as well. So now I have really hot water. At Earth's surface, this would be at 100 degrees C. I'm going to take the heat away. Keep taking heat away. That's going to result in our water cooling off, right? Cools off, Cools off, cools off, cools off, until I get to this point right here. What happens there? Freezes. So not only is this the melting curve, it's also the freezing curve, depending on which direction I'm going. So now we turn it into a solid. What happens if I keep removing heat?
Just be more solid.
It's just colder ice, right? And eventually we end up at B. Okay? Again, you guys have seen various aspects of this out in nature. All right, let's go a little different direction though. Let me get rid of that. Rid of that. Let's start right here. A. Now we're going to do something a little different. We're going to keep the temperature exactly the same. We're going to keep it at this temperature right here. We're not going to add any heat. But we're going to squish it. Okay? We're going to add more pressure to it. How am I going to move on the diagram? I'm going to move straight up. Okay, so I'm squishing it. What happens when I get here?
More pressurized ice.
I have ice that's under a little more pressure than it was earlier, right? Let's add some more pressure to it. What happens right there? It hits the melting curve, doesn't it? Now, that is something that's really unique, and water is the only substance that I know of that actually does this. When you squish it, it melts. That doesn't really make sense according to what I've talked about already, right? When you add pressure, that makes it harder for atoms to move around, right? But I just added a bunch of pressure and my atoms started moving around. That's because water has a really goofy geometry. It's something we're going to talk about next class. It has to do with how the water molecule is put together. And it's because those water molecules, they have a weird angle and you can't make a good geometry out of them. So when you squish them, they're always shifting around, moving around like a liquid. Now the cool thing about this is this property, and if I squish it some more, I'm just going to be in the liquid. So I've created a liquid by squishing it. All right? That's really unusual. Most substances don't behave that way. I'm going to draw you a phase diagram for just about every other substance out in nature. So here's pressure, here's temperature. That part looks the same. There we go. So we have solid, liquid, vapor. This is for most substances, and this is for water. What's the difference between water and most substances in terms of the phase diagram? That freezing melting line, instead of going up and to the left, goes up and to the right. And what that means from a more practical standpoint is there's nowhere that you can go in this solid field and increase the pressure and end up with a liquid, right? If you squish any other solid besides water, it stays a solid, which makes total sense, right? When you confine atoms under more pressure, they have a harder time moving. Water is weird. Water is just weird, 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 which means under pressure, it can turn into a liquid. Now, I use this example all the time. What if I put on a ice skate right now, took a running start and tried to glide across this floor or across any rock? What's going to happen to me?
Catch friction.
I'm going to catch friction and I'm going to land flat on my face, right? But what happens when I do that on ice? I get this great glide, don't I? What's going on under my skate when I put it on ice that's different than I put it on any other solid substance? Is there pressure under my ice skate blade?
A lot of pressure.
If you don't believe me, I will go get an ice skate. I'll strap it to my foot. You can put your hand down on the floor out here, and I'm going to stand on it with my ice skate. All of my weight is on that tremendously small surface area under the skate blade, right? And what's happening under my skate blade is I'm creating enough pressure to move into this liquid phase. So I'm getting a little melting under my ice skate blade. That liquid reduces the friction, and I'm able just to glide on a little layer of water that's created under my blade. What about glaciers? Glaciers are kind of cool, right? What do glaciers do? They're made of ice, they're solid, right? But what do they do on a slope? They move, right? At the base of the glacier, there's actually enough pressure that you start getting little bits of melting that can allow those little ice grains to shift easily and allow the glacier as a whole to behave more like a liquid than a solid. Whole thing doesn't turn to liquid, but there's enough little bits of melting between the ice grains that they're able to shift around, and the glacier can move in response to stress. So this gives water a pretty unique place in the world in terms of how it behaves. All right, one final thing I want to do. Let me get rid of this. And I'm going to get rid of some of this. Okay, let's start right here. A. What do I have? I have a solid, I have a chunk of ice. Like in our first example, I'm just going to heat it up at the same pressure, okay? Where I've positioned this relative to our earlier example is that I'm at a little lower pressure, right? So let's heat this up, okay? Let's start at A and heat it up. How am I going to move? I'm going to move to the right, right? We're going to keep the same pressure, right? That is not where I am. Let's see. Looks like I'm more there. Okay, so I'm going to move. I'm going to add some pressure. I'm going to add some heat, excuse me. All right, let's heat it up. Hotter, 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 hotter. What happens right there? I go from a solid to a gas. And then if I keep increasing the temperature, I just get hotter and hotter gas. Anybody know what that process is called?
Sublimation.
That is called sublimation. So that part of the curve is called the sublimation line. If you want a good example of a substance that sublimates here on Earth at our pressure and temperature, dry ice. Solid CO2, when it heats up, it turns right to a vapor. No liquid. That's why I call it dry ice. It's cold, but when it heats up, it doesn't get everything wet. It just goes straight to a gas. What if let me get rid of that. What if I start here and do the opposite? Take heat away at the same pressure. Which direction do I move? I move to the left. When I hit this point right here, what happens? I turn from a vapor to a solid. It's called deposition. Now you guys maybe have seen the first part of that example with dry ice. But you notice it can happen with water, can't it? Water can behave just like dry ice behaves. But right here, this would represent the surface of the Earth. That's our pressure, right here. You can see when you're on the surface of the Earth, we always have enough pressure that we have 3 fields that you're going to encounter if you heat up ice. If we want to get to a place where water will go directly from solid to vapor, what do we have to do? You have to lower the pressure quite a lot, right? It can happen at the highest elevations on Earth. You go to the top of the Mount Everest, you can get sublimation up there. The other place, because I love studying planets where this happens a lot, is Mars. Mars does not have enough pressure to have liquid water present on its surface. But there is liquid water at Mars. Where is it? You have to have more pressure, right? Where do you find more pressure than on the Earth's or on a planet's surface? In the interior, where gravity is pulling down rock and soil and debris. So if you go to the interior of Mars, the pressure goes up. So we likely have liquid water on Mars. It's just not on the surface. And if we need liquid water for life on some of these other planets, like Mars, we're not likely to find it on the surface, but we could find it at depths beneath the surface. So it's possible if we go to Mars and start digging around, you have to dig down maybe 100 feet or so to get to the right pressures. It's actually possible there could be a fair bit of life, but it's all subterranean. So kind of an interesting way to think about it. All right. Do you guys have any questions on this? Okay, take about a 10-minute break and then we'll do a little more and then finish up.